Welcome. My name is Abel Sanchez. I'm sitting here with Francisco Martinez, who is from a beautiful region in Spain. If you've never been to the south of Spain, you haven't been to Spain. So with that, let me ask Francisco to share with us a little bit of the work he is doing.
Hi, Abel. We do molecular modeling. We try to design new materials from the molecular scale. Okay. We try to understand how the different building blocks of materials contribute to the overall properties, and how can we tune these building blocks to design the properties we want for different applications.
So it's quite interesting. He was explaining to me at a low level what he is doing, and he's actually modeling at a very fine level of detail, which imposes some expensive computation. And maybe you can mention a little bit about what the limitations and how it is that you carry out this modeling in the computation.
Yeah, actually the kind of models we use are always defined by the computational cost. Mm-hmm. So ideally we would be able to design the materials very accurately using including the electrons, the atoms, everything in the model. But the problem is that when we have a lot of different units in the system, which means a lot of electrons, a lot of atoms, this makes the system very complex to solve. So then we have to use approximations. Let's say the story of the molecular modeling is the story of an approximation continuously. And so then it's part of the job is trying to define, okay, for this model, for this system, for this size of the system, what kind of method do we need? And then we use more approximate methods or less approximate depending on the size of the system. If we are dealing with proteins, or we are dealing with molecules, or we are dealing with bulk materials. This is usually made in computational clusters with thousands of processors. Yeah. But then, we don't have a lot of access sometimes to this kind of clusters, so we have to deal with many other people using them, so we have to be very clever when choosing the model, choosing the kind of resources we want.
So very much like most fields today, a lot of the problems become computational problems. I was struck by what you mentioned, the time scales, and you mentioned the impact of moving beyond a certain barrier or beyond a certain number, and I was again struck by the level of time that you can look at. So maybe you can comment a little bit more on that.
Yes, when we are, in real time, when we want to solve systems of thousands of atoms, calculation like this might take days, depending on the level of theory you want to apply to the system. In the time of the model itself, when we are trying to model the dynamics of a protein or the dynamics of material which is under pressure, we want to model how it breaks. In the time of the process itself, we are able to model only picoseconds or nanoseconds. Which is good enough, because if you think about it, the failure mechanism at the molecular scale takes place at this time scale. When the atoms are breaking, it's a very, very fast process. So the time scale we're able to model is in agreement with the time scale at which this process is happening. So there's a kind of agreement, even though we would love to have seconds, minutes, or hours to really model how the process is happening at the macro scale.
So that's certainly impressive, the amount of understanding that you can get and the amount of resources that you have to utilize simply to look at these small snapshots. You were also commenting on the work you're doing on an asphalt and the materials that you're bringing to it, which I thought was fascinating, and certainly given the utilization of resources that we're taking in the world today, and also the variability within asphalt. You mentioned something that I found interesting, that the poor understanding that there is in asphalt and the materials that you could bring to give it extra properties. So maybe you can mention a little bit about that.
Yes, so asphalt is a very interesting material. The problem with the understanding about this is asphalt is a leftover from petroleum distillation. So you remove everything you find interesting, like gasoline, kerosene, and many other light compounds that we use for developing polymers and many other materials. And then we have a leftover in the bottom of the column that we just put it on the road, and it works. And because it works and it's cheap, there is no really a need for understanding how it's made at the molecular scale, how we can improve it. But nowadays there is a growing interest on trying to understand how is asphalt to make it better, to make it more sustainable, to make it more economic when you apply it, to use less energy, what is called warm mixes, to apply it at a lower temperature. So then that's why we want to understand how is asphalt at this level. But the problem is because it's leftover of, once you remove everything, you have a bunch of different types of molecules. So it's impossible with the techniques we have to characterize this specifically what kind of molecules you have there. So then what we do is we classify the molecules in different types, even though we don't know the exact composition, but we can say, okay, we have 4 families of molecules in here, and we try to create a model that represents, on average, these 4 families. So when we know we have kind of an average representation of the 4 families, we can model how these families contribute to the properties as building blocks. And then if we know the 4 families, how they contribute to the properties, we can try to find similar molecules out there in waste or in other sources. And then we can try to design new asphalt using these building blocks. The reason for going look for it in waste sources is for two reasons. One is to use this waste that otherwise is unuseful. The other thing is purely economics. So if we want to compete with the asphalt coming from petroleum, which is so cheap, we have to do it as cheap as it is the asphalt. Because otherwise, I mean, no one is going to invest on something that they can do it very, very cheap if we want to do it with very advanced materials. But if we are able to do this same asphalt from waste, doing it more sustainable and also equally cheap, then we are price competitive and we can really develop the material and put it on the roads.
So that's quite interesting, and I mean, you can see the potential. You can all start to imagine that depending on the road that you have and the type of usage that it's going to have, you could provide a very different performance when it comes to asphalt, and that's certainly, I would imagine, just like it is for cement and other things, it could become a quite interesting market. I think one of the comments I'd make is that people talk about the changing face of civil. We are within civil, and this is, I think, representative. You have computation, you have chemistry, you have all these different techniques that normally people think of civil and they think of roads and they think of bridges, right? But it's quite a different environment today, and people from civil do everything you can imagine.
Well, I think that the reason for that is also something in agreement with the time. I mean, nowadays we have different techniques within nanotechnology that give us the chance to really design and change materials at the nanoscale. Like before that, engineers were people building bridges, roads, and more infrastructure at the bigger scale, which we still do. But now the new engineers, they can also provide these kind of materials, these kind of designs, but they can start this at the very bottom scale. So there is a bottom-up approach of engineering that goes from the molecular scale to the big engineering materials, and this kind of big engineering at the very narrow, small scale, I think is a new concept of engineering, which goes with the new techniques, with the new nanotechnology that we are developing, and that, I mean, it's logic that we go with the times in this kind of
it's fascinating because it's so interdisciplinary, and at the same time it's using techniques that are evolving, around the institute. And so this is obviously a great place to do it, just because there's so many other groups around doing so many different powerful techniques that we can borrow from each other and solve problems in new and interesting ways. So I think with that, I'll thank you for stopping by, and I hope you found this interesting. I certainly did.
Absolutely. Thank you.
So thank you, Francisco.